Good morning, one and all. Welcome to this gathering. And also, I welcome you to this talk in the series, in the Coffee with Curiosity series. Today, this talk usually used to happen in the evenings, but for some reason, we have kept it in this morning. JNP, as you know, has been organizing many science activities, both in non-formal education program and also science popularization program. And every month we have many programs. This month, on 26th, we have a special lecture series which was started 2 years back, which is called as Dasara Lecture Series. The theme of the Dasara Lecture Series of this year is Origins. So we have 4 very popular lectures and given by very, very eminent speakers. I just read it out, and please make a note of that and please attend those lectures also. Origin and Evolution of the Universe on October 26, Saturday, 4 p.m. Professor G. Srinivasan of RRA will be speaking on this. Origin of the Earth on October 27th, Sunday, 4 p.m. The speaker is Professor Ramanand Chakraborty of Indian Institute of Science. On November 9th, the title of the talk is Origin of Life, and it is by Professor Vidyanand Jundaya of Center of Human Genetics. And on November 10th, the talk is on Origin of Material Properties. The speaker is Professor S. Ramakrishnan of Indian Institute of Science. So please attend these talks. Now coming to the this talk on Coffee with Curiosity. So it is on 26th and 27th, here at JNP Planetarium. Yeah, it is better you register, sir, because we will know the number, right? So you can contact us, any of us, for registration. And it is also available, the link is available on our website. So now, I welcome Professor Shankar for introducing the today's speaker and also talk about the Coffee with Curiosity program.
Thank you, Professor. So, great pleasure to introduce a colleague, friend, mentor, and also teacher sorts, Rama Govindarajan. Although you haven't really taught me in a classroom setting, but I've been to your lectures when I was a student many years back to give this talk. It's also, as you will see, at the end of 45 minutes or so, it's also with a sense of envy that I introduced Rama. That's because, so all of you have smartphones, so you will see her Wikipedia page, you know her trajectory. She was at IIT Delhi, she did a PhD at IISc, then she had a stint at Caltech. She worked for years at NAL, Jain CSR, then TIFR Hyderabad, and now at ICTS. Well decorated fellows of academies, various prizes, but I'm not going to talk about that because that you can check up, all of your smartphones. What I will talk about, which is probably what you won't find in her Wikipedia entry, I suppose, is the fact that Rama is unique in many ways, and that's where the envy comes in. She's unique, as you can see from that subtitle up there on the screen, in asking questions which are, which go to the heart of that matter. And these are questions which are driven by an immense sense of curiosity, more than, I haven't seen that sort of curiosity in most quote-unquote professional scientists, as it were. And that combines, and again, you will see that in her talk, I'm sure, that combines a level of scholarship which spans across different sections of sciences. So it's no surprise that she started as a chemical engineer. She's worked, she's touched on different aspects of engineering, her work on instabilities, on interfacial flows, etc. really sits very comfortably at the interface of applied mathematics, computational sciences, engineering, physics, and most recently, she's sort of looking at particulate flows, which is really, in the so this sort of wide span is something which is really admirable, and it's something that you will see, and that sort of all of this sort of combines in Rama asking questions which are, to put it in plain language, which sort of bridges the world of curiosity that a young person has in the world around that young person, as well as the necessary scholarship which enables a person to answer some of these questions. So, before I let Rama take over, just to also thank the ICTS outreach team, which has, made it possible for this. So Devdatta is somewhere there, so you guys can get in touch with Devdatta Paul. He sort of organizes many of these outreach activities with his team at ICTS. So there is this, this program, the set of lectures called Kaapi with Kuriosity, which happens here typically on Sundays at 4 p.m. Today is sort of anomalous time for this lecture. The next one, I understand, is on 3rd November at 4 p.m. by our friend TNC Vidya, and that lecture will be on ecology and little animals and things of that sort. So do check our website, do check the other outreach activities that Devdatta and his colleagues are involved in, and do drop in also at ICTS for some of these activities. And we look forward to having all of you there for subsequent outreach programs. And more than anything else, we look forward to Rama telling us why clouds don't fall and why we are sort of safe, even though it's quite cloudy outside. Over to you, Rama. Thanks.
So one thing I realized from this introduction of Shamriddhi is that if you want to look much grander than you are, like ask a friend to introduce you. So I'll totally assure you that the envy is the other way around. He's like amazing, but I'm not supposed to introduce him to you right now. So yeah, let's go with this. Today's topic is dusty flows in nature. And so first of all, I want to know how many of you are ever been in a dust storm, seen a dust storm, been caught in an avalanche? One already, 2, 3, yeah, several. Dust storm or avalanche? Dust storm, okay. And so you have a clear experience of what it's like, right? So that's why I added this subtitle. For that matter, why don't dust storms fall down? So like when I was a kid, we had lots of dust storms in Delhi. I was in Delhi, and we believed that these sand particles came from Rajasthan, from the Thar desert. I have no idea whether that was true or false, but they came from a very, very long distance. And every time the dust storm came, we would hate it because we couldn't play. Like we had to run in and shut all the doors and windows, and that was horrible for a child. And then after the dust storm, like in spite of keeping everything shut, in a small house where we lived, we would actually sweep up something like half a bucket of sand or dust. So it's really, really something amazing. So like, why don't they fall down? Like dust particles are heavier than air, right? All those sand particles. So why are they carried all the way from, I don't know, some long distance, Thar desert or wherever? So why don't they fall down on the way? Like why do they reach these great distances? So that's one question. By the way, today's talk has to be a discussion. So I've got, I think, 25 slides or something, but if we finish 5 also, it's okay. So just ask questions and let's have a conversation here. And I've written I've written here much common ground. Much common ground, it basically means that dusty flows, whatever they are, whether it's a dust storm, and we're including clouds in this discussion, we're including a bunch of things. There's a lot of commonality between all these things. So if we can solve one, we can learn to solve for many others. So that's the story that we are going to talk about today. Okay, so here are some examples of dusty flows in nature. We are defining a lot of things as dusty flows, including things which are not technically dust, like marine snow, snow avalanches, and even these prilling towers in industry where like, for example, baby milk powder. It's made, you have a bunch of hot milk which falls down and hot air which falls up, and then these things become little particles. The milk powder becomes little particles, and then there are big questions in all of these. So you see some examples. Can anybody add more? This is a cough, by the way, a human cough. I forgot to put the title there. Anybody has ideas for more things which can come under dusty flows? We've got some more examples in the next page. Any thoughts? Okay, we'll be talking in a little detail about marine snow. We'll be mentioning something about snow avalanches, and maybe cough, like we can discuss it if we have time. But some of the things that we talk about will be common between these. And here are some more examples. Okay, one guess, which city is this? Delhi. Good guess. I yesterday saw some pictures which are of Bangalore, which don't look too different. Okay, but this is something I've actually seen. Okay, so there is this big 10-story building which is there, like just one street away. I mean, just across the highway from where we live. And there are times of year when you cannot see the 10-story building. It's that thick. Delhi. So yeah, it's really bad. So like, I think all young scientists in this room need to start worrying about things like this and start solving some of these problems. And tsunami, maybe like many of you here were not born when the big tsunami happened, or maybe you were too little to understand it. So yeah, there was this big tsunami in 2004, right? Yeah. And so what a tsunami does is it brings like big rocks and things like, I mean, they're not dust, but we are defining dust very broadly. It brings big rocks and lots of ocean bottoms mud also, and throws it onto the earth. Okay, so just to give you an example, like I'd been to a village near Pondicherry, somewhat 3 hours from Pondicherry, and just after the big tsunami of 2004, and we had to, so when we went there, there was a mountain of rubble, and there was a whole bunch of volunteers who'd come to help clear this place. So like we started digging into like many feet of mud where, we found lots of horrible debris of all kinds. And after the whole day of digging, we could see that the real floor of the temple where we were digging. So it's that amount of stuff which is brought in. So that's another kind of dusty flow. There are more examples. Here I put GPGP as a hint. What is this? What? Yeah, this is an ocean current, very correct. That is garbage. Okay, 1G stands for garbage. Great. Then, what else? What does the other G stand for, and what does the P stand for? Anybody? Any guesses? It's the Great Pacific Garbage Patch. I don't know whether it's the Pacific here. Yeah, it is the Pacific. Yeah, it's a Great Pacific Garbage Patch. And I don't know, on the internet, I mean, Shamriddhi was selling the internet to you at great length, but I saw this picture which claims to be the Great Pacific Garbage Patch. I don't know whether the garbage is that dense over there. I think it's a lot more dilute, but there is a patch where so much garbage is collected that any ship going through there can see it, and it's really terrible. We put microplastics and big plastic bags and all kinds of horrible things into the ocean. And that's what humans have done to the Pacific Ocean. And yes. Good question. It's very hard to clean. It's like, it's got a radius of thousands of kilometers, right? And it's like dilute. So you need ships and you need lots of energy to, I mean, and the energy, that may be a bad thing you're doing to the environment, trying to clean this up. So I think the best idea is don't put it. Don't put it there. Like, I mean, that's the best idea. But yeah, like, I mean, we're not able to clean up Bangalore.
Reach to some other place from that particular patch or something.
Okay, how would you do it? There are, I mean, these ideas are being talked about in geoengineering. Yeah, but you have any thought on how you would do it?
Because it's in the ocean, like floating, maybe some sort of current to like push it towards one particular direction, and maybe like some sort of barriers so that it like flows in some direction, and then it can be sorted out and cleaned.
Quite possible. Like maybe you could. I mean, many things which sound bizarre are actually possible. Okay, and people are talking about that in geoengineering for climate change. So one, yeah.
Plastic or garbage.
Yeah.
Reuse this
Exactly.
garbage. So future this young people should work towards that direction.
Exactly.
Otherwise, no. Even after 10 years, this all sequels will be like this garbage. Yes. Yesterday, I saw some lake going for walk. So much garbage is coming, and municipality people they are not doing because each individual should work on.
You're quite
This should
right.
not
Like,
blame government also.
you're quite right. Like, rather than throwing it in the ocean, we can do better things. Like, yeah, the first thing is don't put it there. Like, do something else with it. Yeah. I know, if you're recycling it, you won't put it in the ocean. That's what I'm saying. You won't throw it in the ocean.
Way to like some.
So it's drifting into that place from everywhere.
Okay.
Because of the way the currents are. So like now to design something which will, maybe in some time of year, the current will be in certain direction and you can put barriers to collect it. Things like that may be possible. Who knows? Like your generation should look for those things. Okay, so this is an ISRO product. So ISRO gives nice products which, if you're a student or somebody working in certain places, you can actually get an account, a free account, and you can download this data and play with it. So if some of you are good in AI or things like that, you can try to download. So like what you can do is, so this for example is some 20th November 2003. On that day, like what was the aerosol over India? And as usual, you see like North India is very bad. And this is a big portion of North India. Like it's easy to say Delhi, it's not one city. There's a lot of pollution or, smog and things covering the whole of North India. So like if you can use AI tools to understand how this is coming, where this is going, there's a lot of research to be done here. So this is one point I want to make. Okay, so this, before I show the movie, I'll tell you what it is. This movie is supplied by Jim McElwain, who's my friend. He does work in snow avalanches. So basically, this is some very, very, very unpopulated region of Switzerland. We don't have such regions here to my knowledge. So what you do is like, he's got this little helicopter in which a pilot will fly, and the pilot will drop some TNT, like basically a bomb in this place, and that will create the snow avalanche. So then they can measure the snow avalanche at different places and understand like how far it will go or what will happen. So let's watch the movie. It's some German thing going on. Yeah, you see the bomb? Saw it? Do you see the snow coming down? It's actually very noisy. Can you see it? It's very white, but it's there, see? It's almost like a river coming down, na? And you can see the size of it. It's a human-made avalanche. Yeah, you want to see that once more? Yes, no, maybe. Oops. Let's see it once more. You can't see the pilot, but you can see, there he threw the thing, you can see that. And these people sit downstream and they take many measurements of this. Okay, so the idea here is that the basic thing here is that there was no airflow, almost no airflow before the bomb was dropped. Okay, so we're talking about a dusty flow, we're talking about air which is carrying the snow particles, right? So, in the dust storm and all, you can imagine that there's a big gust of air which is then picking up the sand which was sitting still in some place and bringing it to another place, right? So that is different from this, where the air was not responsible. The bomb was dropped. The bomb is small relatively. Like, you can't create this huge thing with a small bomb, right? Like, they threw a small bomb and it made a small bunch of snow. It made it fluidized, like the snow got into particles and started moving with the air, a small amount. And then this, as it comes down the hillside, it's eroding more snow. It's eroding more and more snow, and it's becoming a big avalanche just because potential energy is getting converted to kinetic energy. So like, it's becoming bigger and bigger as it goes down. And I've seen some movies where, not this one, he didn't do anything, but there are movies where snow avalanches have actually buried villages. So this is another kind of flow. And this mammatus clouds, we're going to talk about clouds in general, but I've just made a collage of some of these nice patterned clouds. In my first slide, I've given my email ID. It's rama@icts.reg.in. If you see a mammatus cloud or an asperitas cloud, like, just take a pic and mail it to me. I've actually got a collection, and somebody can actually make a little album out of it. So this was seen in Visakhapatnam on a certain day, but in Bangalore also we see mammatus clouds. Keep your eyes open. So it's almost like these bulbous things hanging down. Yes? Somebody had a question? Who's seen it? 1, 2, 3, 4. Yeah, lots of people have seen it. Yeah, so others also will see it, hopefully now. Okay, so just 1 minute on a cloud, because we're going to be talking about a cloud. It's better to pin our thoughts. Like, what happens in the atmosphere is that the temperature keeps going down, down, and down. Okay, when you're in a flight, like, at what height are you flying typically? 6,000 feet? 36,000 feet, 10 kilometers, let's say. What's the temperature there? -2 in what units? Degrees Celsius? No, it's -40 or something. It's like super, super cold, like just 10 kilometers above. And I like to say this to pin your thoughts, like, if I go from here to halfway to Jayanagar, suppose the temperature is falling by 70 degrees. How will that be? And that's what happens when you go halfway to Jayanagar, but up. And that's the huge gradient in temperature when, you climb up. So the plane flies like somewhere there. Planes fly somewhere there, which is like -40 or so. It's like around 10 degrees per kilometer, a 10-degree drop per kilometer. So that's what happens. So what happens is that on the surface of the ocean, things evaporate because of sunlight. There's a lot of water evaporating, and this forms little blobs of warm, wet air. This thing, because it contains a lot of water vapor, and then because it's warmer and it contains water vapor, it's lighter than the surroundings. So it climbs, climbs, climbs. And that's a story for another day. Why does it climb? But once it reaches that height, which is called the lifting condensation level,
I have told
at
them
that height,
12 noon, I will signal them.
hello? Oh. So once it reaches that height, so there is nothing called a lifting condensation level, which is a golden line, okay? It depends on how much water vapor is there in a given gust. So like wherever it reaches saturation. So like who knows how saturation changes with temperature? Is water more saturated at low temperature or high temperature? At low temperature, the same amount of water is more saturated. So in case you forgot that, in case you forgot which way it went, you can ask yourself, like, if you hang out clothes to dry, like, will it dry better on a hot day or a cold day? So one guess, it will dry better on a hot day, right? So on a cold day, like, it takes a long time to dry because the water vapor doesn't escape very easily. So like things like to remain as liquid water when it's cold. So that's like a normal cold day, but here you have like, you know, very, very low temperatures. So whatever water vapor you have will be saturated, and then it likes to be liquid water. It doesn't want to be water vapor. So when it wants to be liquid water, what happens is that it looks for somewhere to condense on. So the air is like super saturated. It wants to condense, but unless there are solid particles, it cannot condense. So whenever you have like aerosol particles, so these red things are aerosol particles. The atmosphere is full of aerosol particles of different kinds. And then these aerosol particles become nuclei and the water condenses onto that. And then you get liquid water drops. And typically these water drops grow till about 10 micron in size. And when they're 10 micron in size, they scatter light and you see white color. You see the cloud because it contains lots of 10 micron. I thought before we continue the rest of the lecture, we should address the question of why clouds don't fall down, and then we'll proceed. So that's why I'm giving this background. So are aerosols good or bad? I've already given a hint here. Bad? Good? Yeah, depends. They are good and bad, so there's no wrong answer. They're bad because if we put too many of them in the atmosphere, we saw what happened in that photo of Delhi, right? And they're good because without them, there would be no rain. And this also gives us a hint that, wait, aerosol is not all man-made. Because if it was man-made, you will never have rain. And rain has been happening for millennia. Rain is happening on other planets. So for rain, like you need aerosol. So clearly there was aerosol before we guys came along, right? So where did that aerosol come from? It could be these sand particles which were carried to great heights. Like in a dust storm, it's carried already to big heights, and it could be like tinier ones can be even picked up and taken to even greater heights. Sea salt is a very, very important aerosol. So like when the ocean waves crash, like there's evaporation going on all the time, and these droplets are carried to great heights by the wind, and when they dry, like you have tiny, tiny particles of sea salt. And that is usually the reason why it rains like crazy on a pristine ocean. So you can have rain on a pristine ocean, right? And that's because of sea salt aerosol. So yeah, like some aerosol is good within limits. Okay, so this is simulations of a cloud. Whatever I told you in the previous story, you'll see in this. And this is a simulation using this lovely code called Megha, which is designed in Narsimha's lab, and Ravichandran, whose photo is here, he is a prof in IIT Bombay now, and he is one of the writers of this code. So like this code can solve for cloud flows. We'll see a movie of it. We'll see 3 photos of the cloud here, here, and here. And here, I'll tell you, I've forgotten which way it goes, but the last one is of water vapor, how liquid water. The last one is about liquid water. So let's watch it. So yeah, the first one is the velocity of this blob that I said is climbing, right? It's climbing effectively from the hot ocean. And the second one is temperature. You see it's hotter than the surroundings. And you can see liquid water coming up only at a certain height, like it doesn't come from the ground because it has to reach the temperature at which it can condense. So the temperature is falling as you go up, sorry. So you see the cloud forming. And you didn't see these parts. You didn't see the velocity and the temperature, but you saw the liquid water because it's scattering light. So it's not visible, but you can see it. Okay, so this gives you an idea of how a cloud forms. Any questions on this? Any at all? Yeah.
From water again, I mean to the point where it has become liquid again, the temperature has risen again.
Yeah.
That is kind of contradictory to my intuition. I thought it will become colder and colder. So
Very good point. Very good observation. The point is the following, that it is becoming colder and colder. We've hidden that. We're plotting only the deviation from the background. A. So we're plotting only like, so all of this which looks red is actually colder than this place. We've subtracted the local temperature. So it's warmer than the local, that's all. That's what this is. That's point number one. Second point is that whenever condensation happens, latent heat is released. So it warms up the environment. Actually, as there is more and more condensation, it warms up the environment. It's the opposite of evaporative cooling. So that is actually happening to some extent. Great question. Okay, so why clouds don't fall from the sky? We're now ready to answer that question. The point is that water droplets are how many times more heavy than air? What's the density of air? What's the density of water? Tell loudly.
I'm not sure if it's right, 1,000.
Density of water.
1 gram per centimeter cube.
It's 1 gram per centimeter cube. What were you saying?
1,000
1,000.
kg per meter cube.
Yeah, it's 1,000 kg per meter cube. That's correct. So 1,000 kg per meter cube is 1 gram per centimeter cube. So yeah, it is 1,000 kg per meter cube, and air is 1 kg per meter cube. So water is 1,000 times heavier than air. That's a good number to remember. It's 1,000 times heavier than air. So like, I mean, if I keep a cricket ball here, it will fall, right? Like that, water droplets also should fall. So why aren't they falling? So that's a question which we need to think about. So there are two answers to this. One is, A, they are falling. All clouds are in fact falling. But B, there is air drag. Who studied Stokes' equation? Yes? I'm not keeping a test on it, so you can happily say yes. Yeah. So like, you know that if you're a very, very small particle, then there'll be significant drag on you falling. So like your speed of falling slows down a lot. So the teeniest ones are falling, but they're falling like really, really slowly. That's one point. The second is that the minute they fall out of this cloud, okay, like they've fallen out of the white line and they've come to the blue. So there, like, it's undersaturated, right? It was supersaturated only at cold temperatures. Cold temperatures are higher, right? So it's fallen from there, means what will happen to it? Once it's reached the undersaturated place, what will happen? Huh? Yes, it will start evaporating. So like very, very soon it becomes smaller, 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 and very, very soon it's all gone. So those tiny drops actually can evaporate within a meter or two of falling. But then they'll wet the environment, and so the whole cloud will slowly descend, but super, super slowly. Got this? So yeah, that's why there is a boundary, because once it gets warm, the water droplets can't live there. They're very tiny and they'll evaporate very fast. Okay, so we got why clouds don't fall from the sky. Why this problem is hard? Don't panic. I think this is the only slide with equations. So, and you don't need to understand them. So don't already leave the room or something. Yeah. So why is this problem hard? So like we know the equations, we know everything about it. There's no, you may think there's no science left because we know the equations, but that's not true. And the thing is, even though we know the equations, we can't solve the equations. That's the thing that I'm going to explain in the next few slides. So like if we can't explain the thing, like if we can't solve for it, then how do we go about understanding anything at all? So this is the question that we are going to ask in the next few slides. Okay, how many of you do not know the Reynolds number at all? Everybody knows Reynolds number? Okay, 1, 2, 3, yeah. So there's several people who don't know. You don't need to know it because I'm going to tell you what it is. So this RE is a number called the Reynolds number. And in fluid mech, we like working with non-dimensional numbers because it simplifies our thinking a lot. So like if I just write down the number of parameters that are varying in the cloud or the number of parameters that are varying in any problem, then my head starts getting swimming and I don't know like how to approach that problem. So the first thing we are taught to do is write the equation in non-dimensional form. So here we have a cloud, it has a length scale, there's a velocity scale which is churning it, there is viscosity, there's many things going on. And whereas if you write the equations in this form, there's only one unknown, which is the Reynolds number and the boundary conditions. So like I've reduced all my, a large number of my variables into one variable, one non-dimensional number. So there is this theorem called Buckingham Pi theorem. How many of you have studied it? 1, 2, 3. Go back and read the Buckingham Pi theorem again, or if you have not read it, read about it. You will see how you can simplify a problem and know what is the minimum number of non-dimensional numbers you need to work with. And then the whole problem can be defined in terms of that. The other benefit it gives you is that suppose like before we started this lecture, me and Mr. Madhusudana, we were discussing lava flow, okay? So like he was asking, can you make lava, are you sure you're making the right lava in a lab? So we are actually making it with candle wax, and the candle wax is melting and flowing down a hillside. We made a little hillside and it's solidifying. You had a question? You had a question? Huh. So it's solidifying. Okay, and this is a model for what's happening. This is solidifying in seconds, like candle wax, if I pour it will solidify immediately, right? Whereas the real lava which is coming out of volcanoes and all and other eruptions in the ground, it's going to solidify over many, many years. So, and it's very big. So how do I understand anything about it? By doing this tiny little thing, by making sure some of the non-dimensional numbers match, and by making sure that I know what I'm not matching, so I know what I'm not getting right. So in these ways, we can scale up and down a problem to study it. So for a virus or something, you want to scale it up and study a big virus in the lab. Whereas for lava, you want to scale it down. So the non-dimensional numbers are very, very useful in fluid mechanics. This is the Navier-Stokes equation. I put 3 pluses next to it, not to resemble C++ or something, but because there's other physics going on. In many of the flows, you may have to solve other equations. So U is the velocity and P is the pressure, and this is called the continuity equation. These two equations, this one says that basically that mass can't be created or destroyed and the flow is incompressible. So like whoever comes in, that much should go out. That's what this one tells you. And this one is just Newton's laws rewritten for a fluid. It's a very complicated bunch of equations. It looks very simple. It's actually 4 equations and 4 unknowns because there are 3 components of velocity and 1 pressure, and there are 3 equations hidden here. 3 space equations. So it's this thing. So it looks as if, okay, I know the equations, and in clouds, Reynolds is greater than 1. So that means it can be 10 to the power 8 even. 10 to the power 6 at least all the time. Okay, it's very, very big. And I've defined 2 Reynolds numbers here. One of them is this Reynolds number of, let's say, the cloud where L is the typical size of the cloud, U is the typical velocity in the cloud, and nu is the kinematic viscosity. Okay, and the other one is the particle Reynolds number. So the droplets and other particles which are in there, their Reynolds number can be very, very small. And I'll tell you in a minute why it's important. So this V is particle velocity and you're subtracting fluid velocity. It's only the relative velocity that matters. And A, the particle size is in 10 micron. It's very, very small. So this number can be as very, very small, close to 0. And it can be very, very big depending on whether it's a tsunami rock. Or even raindrops can be 10,000. So why does this matter? So if the Reynolds is very, very high, then like you can basically pretend that most of the time you can pretend viscosity is not important. Not always, but you can pretend this. And without viscosity into consideration, you can understand some gross things about the flow. So like suppose I neglect the particles and only talk about the flow, the viscosity is very, very small compared to its, length scale and velocity scale. So we can understand it by a different kind of physics. And for the particles, it's the ulta, like Reynolds is so very small that I can neglect like this term. I can neglect this thing, and here I have such a small number in the denominator, so it becomes a big number overall. So I can just relate that to the pressure and get a much, much simplified problem. Right? So I approach the problem differently based on what I can neglect and what I need not. Is this clear? You never saw Reynolds number before. So are you getting an idea? So basically we are saying that we can treat the flow in a different way from the particles. So we are now in a dusty flow where there's turbulence in the flow, which we'll talk about in a minute, and then there's particles. So we can treat them differently if the particle Reynolds number is very, very small. So here I've put a photo of a cloud, but remember that this applies to many, many flows. So the dust storm, various things can be studied under certain approximations by the same approaches. Okay, what's turbulence, everybody? Somebody who's not studied fluid mechanics, like fluid mech guys will be biased. Somebody who's not studied any fluid mech, can you tell me what turbulence means to you? Pressure changes. Pressure changes will cause turbulence, yes. What?
Disturbance in the flow is turbulence.
Yeah, some kind of disturbance, like there are certain definitions for which disturbance we'll call as turbulence and which we won't, but typical disturbances are turbulent, yes. Have you seen turbulence? Huh? In a flight? You felt it. Technically, you've not seen it, but you felt it. Yes, probably the most common place you hear the word turbulence is in a flight, right?
Turbulence is not a streamline flow.
Yeah, it's
Other
not.
than streamline flow, because of some obstacles and all, the streamline will be disturbed and the turbulence is caused.
Correct. So like, but whenever a flow is not a streamline flow, we can't always call it turbulence. There's many different kinds of flows which will not be streamline flows, but will still not be turbulence. There's some technical definitions, but broadly we can say that turbulence is where it's very disturbed and very chaotic and very non-repeatable and so on. Next time you hear like turbulence hai belt pen lo or something like that, I think there's no Hindi word for turbulence, right? They say mausam kharab hone ke karan or something like that. Yeah. And in English they say it's due to turbulence due to bad weather. I've never understood that. Yeah, so I've never understood it. But the point is, next time that happens,
Cumulonimbus clouds will be there.
sorry?
Cumulonimbus clouds will be there. They will cause turbulence. So that is the.
Yeah, I guess that's
Weather is meant by.
the cloudy weather. Okay, yeah.
Yeah.
Yeah, that's one way of interpreting it, and that's nice. So yeah, like next time, make sure you have a window seat and make sure that you look out the minute they say wear the seat belt. You'll typically be in a cloud. There is clear air turbulence, but typically you'll be in a cloud. And that's what he was also saying, where there's very bad cumulonimbus clouds and monsoony weather, you'll have to wear seat belt. there's different reasons, but yeah, I don't fully understand clear air turbulence, but it's rarer, much, much rarer than cloud turbulence. So like we've agreed that we felt it, but we didn't see it. But we must have seen turbulence somewhere. Okay, let's go to the next slide. If only we always could see turbulence, you'll see like this is just a man standing there. Okay, now each of you and each of me, each of us in this room, actually at this minute has a plume on our heads. We are not able to see it, that's all. Each of us has a turbulent plume on our heads. Because like our whole body is at some 98.4 degrees, which is typically warmer than the outside. Like I'm not talking about Hyderabad in summer or something, okay? But in other times it's warmer than the outside. So like the air next to us is buoyant and it rises, okay? And because it rises, there's always a plume on our heads. So right now, we are all like engines. We actually got chimneys on us. So the more humans there are, the more we are ungreening the planet. We're just sitting here and ungreening it because we are a chimney. Because we eat food and we stay warm. So that's who we are. So if you could only see it, this is by Schlieren Imaging. This is what it is. In fact, like some 15 or 20 years ago, there was this racket, a big racket, where they said it was called Krillian something, and maybe you all are too young for it, but a lot of people paid a lot of money for this because they were told that, you know, there's this aura coming out of you and we have a way of imaging your aura, and then there are people with good aura and people with bad aura, and then like if you're a person with bad aura, we'll fix you. And if you're a person with good aura, we'll tell you how to recognize people with bad aura and avoid them, or some weird thing. And people were paying thousands and thousands, and educated people were paying like really big money to improve their lives by, you know, understanding the dumb plume over everybody's head. And so like when they saw this, they would get very surprised and they would believe anything that they were told. So like, yeah, that's one thing to remember. We've all seen, you know, some turbulence in some way in boiling water or in a teacup. In the kitchen, we've seen some evidence of turbulence, right? And this is a pipe flow. We'll come back to this pipe flow. Questions? Anybody? Any question? Even on something we've not covered, it's okay. I'm worrying that we're going to finish the talk or something. Hey, Devdatta, how much time do I have?
5-10 minutes.
5-10 minutes? Okay, we'll just talk about one or two things and stop there. Okay, so the thing is, first of all, like very often, because there's not good enough contrast, we can't see turbulence. But of course, like in traffic pollution, we can see like what an auto is giving. When it's giving lots of smoke, we can actually see that. And like this is just flow past a body. You see like so much turbulence. The thing that I want to tell you here is that what is plotted here in color is this object called the vorticity. So vorticity for technical people is the curl of the velocity vector. But in real life, all it means is that in turbulence, there's a lot of rotationality. So you can imagine turbulence being made of many noodles of different sizes, which are all made of air, so you can't see each of them, but they're all spinning at their own rate. So each one is spinning. They can merge, they can kill each other, they can be born, they can die, they can move from one place to another, and they do all these things. So it's a bunch of, you know, snake-like noodles who are alive and they do a lot of dramatic things. So this is the complexity of the problem. And this is just flow past some submarine or something that these guys have plotted. This group does a lot of nice simulations. So the Reynolds number is very, very big, and this is the kind of thing they've plotted.
That generates this vorticity in these turbulent flows.
Okay, so that's not a simple question. The point is that the equations that I showed, the Navier-Stokes equations, they have multiple possible solutions which satisfy the boundary conditions. Okay, they have multiple solutions which satisfy the boundary conditions. Some of them contain a lot of curl of the velocity vector, and especially over boundaries, a lot of vorticity is generated at any solid boundary. That is because of this thing that this boundary is not moving. You have air on it moving. So air is moving at, let's say, velocity u, and this thing is at 0 velocity. So just that difference between here and here, that's a vorticity. Del cross u is big at that place. So it creates vorticity. So that part we can kind of see, but then how does it get organized into these horseshoe-like things? Like literally, if I could see it, it's like a forest on this table right now, no? It's like a forest which has like all of those horseshoes. So it's something pretty amazing. And now, why does it organize into horseshoes? All of that is a lot harder. But it's basically solutions of the Navier-Stokes. So if you run the Navier-Stokes, this comes. There's even a debate on whether these are true horseshoes. So these are not settled questions, but typically it organizes into horseshoe. This is the thing, turbulence in a pipe. So like it's just an image of turbulence in a pipe. So normally when we, so one other thing is like, why does it become turbulent itself? That's itself a question, right? And we don't know the complete answer, but we can say, oh, simple flow, what he called as streamline flow, is also laminar flow, is also a solution of the Navier-Stokes. But after a certain Reynolds number, the flow chooses to take other solutions. Although that one is always a solution, that solution is never seen in real life. You see other solutions of the same equation. And that typically goes into that solution becomes unstable, another solution comes up, which is a technical thing. But the point I want to make with this thing is that normally we think of turbulence as chaotic, random. So like, you know, it's counterintuitive. First of all, it's very counterintuitive because we've all studied Newton's law, right? Like basically, if I'm putting force in this direction, things should move in that direction, accelerate in the exact same direction. So like now I've taken a pipe, I put high pressure here, low pressure here. So I'm forcing it through there. So instead of walking in a straight line, like why are fluid particles doing this, walking backwards, doing weird things? So that itself is counterintuitive. So it's just a solution of that equation, and we can discuss more about it later. But the point I want to make is don't ever think of turbulence as random and chaotic, just chaotic. It is chaotic, but it's got high connections in space and time. So you see this photo of the pipe, right? Like they've actually taken one slice through the center of the pipe and one cross section. Do you see that flat one and the round one? So this is a very, very high Reynolds number experiment. It's there in this paper for those who are interested. And you can already see some pattern, right? It's not completely random. Like, do you see 3 red blobs on the round circle? And they've taken the dominant mode of it. They've actually taken the dominant mode of it, and this is what it looks like. So there is a dominant, hexagonal or some 6 wave pattern sitting in the pipe. And in real pipe turbulence, you'll always see some pattern or other. So it will go from one pattern to other. It will be primarily in one pattern and less in other patterns. And it will be following things like this, but it will not be completely random. So if you analyze it, you'll start seeing a lot of pattern in the flow. So then this is one important slide for me. I can even stop after this, and maybe I'll just show you the pictures in the other ones. So like we think of turbulence as chaotic, random, unpredictable, blah, blah, blah. So like this is a question which people ask in general, that if everything is so unpredictable, how do we know climate is changing? It's just doing its chaotic thing. How do we know it's going to get warmer? It may be getting colder because it's unpredictable. I mean, how are you even predicting, right? That is the important question in everybody's mind. But we are predicting climate change, right? And how are we doing that? So, in fact, Kasselman, one of the people who won the Nobel a couple of years ago for climate, he actually showed many years ago, like when it wasn't even clear. I mean, now it's so clear that Earth is warming, like every data is telling us that. But decades ago, when it was not even clear, he found like very good mathematical techniques. So turbulence is like chaotic like this. He developed a mathematical technique to find a teeny tiny trend in that. How do we separate this and actually positively say there is a trend? And it's not just noise. So the noise is so much bigger than the trend, but he could actually work out the trend. So this is a very, very important thing about turbulence that you should remember. In particular, in a pipe, we know our water bill, right? Every month it will be like plus minus 10% or something. It will not be 50,000%. So clearly we're predicting something about turbulence. We're pumping up water like in this building, some 2 floors, but we're pumping up water on a daily basis. So the point is we know the mean. We know the mean drag, which means we know the mean power needed to push it up. So we can't predict exactly at that point, at that time, how much is the velocity. But we know on an average, it's going to be like this. We know the average profile in turbulence. We know its standard deviation. We know its every higher order moment. We know everything about it statistically. So that's the reason we can predict. Okay, and so like just because we know our water bill, we also know the climate is changing. It's the same idea. Okay, so this is all, the rest of it is about, how complicated it is to solve for turbulence when there is particles in it. So like, even if you put a cylinder in it, it looks so bad. And this is a point he brought up, saying that if I place a cylinder, then there's a very big turbulent thing behind it. Think of thin rocks, think of rocks brought in by tsunami. So these are all the things that I wanted to talk about, and just to give you a feeling for how bad is cloud compared to just Navier-Stokes, and how big are the scales. So the moral here is, A, it's very complicated. B, no computer on earth can solve it right now. So we need AI, we need some more and more imaginative things to solve it. And this kind of grid that we need. So normally you take a differential equation, you make it a difference equation and solve it on little grids. The number of grids you need is mind-boggling. You just can't solve it. And if I want to put boundary conditions on each particle, there are 1,000 particles in every cc of cloud. Forget it. So how do we do it? So I've given some things here, and the basic idea is that we have to do some pen and paper work with easy things, easy subsets, and then scale it up. And then like we can understand some nice physics also. And this is a thing that maybe I'll just take a minute or two to finish about this. It's about how carbon sequestration is done by plankton which are sinking in the ocean. So like, so this is a photo of the sinking phytoplankton. I can answer more about this. And this is experiments of my friend Melissa Omand, who has actually like made a saltwater tank. These are real phytoplankton she collected from the ocean, the Pacific Ocean. And then she's like putting them in a lab tank and seeing how they go reach some, when in some saltwater thing, they settle for some time and then they fall again. And we made some experiments of particles falling through. In fact, Divya day before yesterday, she submitted a PhD thesis, and she'll be going to Harvard for a postdoc. She worked with Tomek and Beverly in Stanford, and we did this experiment on just a falling ball. So it's just a falling ball, and we found some new physics in it. Namely, we found a vortex ring next to the ball at early times. And this is Harshit. He's done some excellent work on how you drop a ball, you expect it to fall, right? Very viscous flow, you expect it to fall. But he's shown that if you just change the shape of this, then like what's the kind of thing it can do. So this, it's falling, we're falling with it. And this is the kind of behavior it does just because of its shape. And it's falling in honey, so there's no turbulence there. It's falling in something way more viscous than honey. It's falling in mineral oil or something like that. So it's 0 Reynolds number, but yeah, it can form very predictable patterns. And this is a quasi-periodic behavior. And Harshit has also shown that you cannot get chaos in a very viscous thing. It's cute, right? Yeah. Yes.
So this pattern that we're seeing, this very uniform pattern, this is in mineral oil. But
Okay, this is a simulation.
okay.
But we are going to see, I mean,
But like
we'll
we're taking the
see.
viscosity of something like mineral oil. Right?
Yeah.
But in the previous slide, you mentioned like there are some fluids where interparticle interactions can be unpredictable or something like that.
Yeah. Okay, yeah, sorry, I forgot to mention this. Yeah, what were you asking?
No, so what if there's a fluid where there's some interparticle interactions and stuff? It's still a viscous fluid, but will the pattern be uniform?
Very good question. Very good question. So the point is, like, here's one particle that's falling. Okay, typically in zero Reynolds number, it will look like this. So this particle is falling, it's pulling the fluid with it. It's dragging some fluid with it. So suppose I have another particle in the neighborhood of this particle. I'll be dragged down because of that guy falling. And if I'm also heavy, I'll drag that one. So we both will interact to pull each other down. So here I wrote it can be different because we saw this vortex ring, right? So in this neighborhood, like if I'm falling, then my friend can be pushed up because of the vortex. So funny things can happen. So you're quite right that when I have a thing like this, left alone, it's making all these beautiful patterns. But if there are two of them, anybody's guess. And you might get chaos, like when you have two or three of them, although the equations are now Stokes equation. I told you we're neglecting the U dot grad U, that term in the Navier-Stokes. But the boundary conditions can make it nonlinear. So I have to satisfy boundary conditions on many complicated bodies. So then it's anybody's guess what's happening. So you might get nice mixing and other things. But it's fun that you put one body and you're actually getting like various interesting dynamics. One of them is this.
So like if we consider more particles, it'll become like a fluid mechanics three-body problem or
Exactly.
Okay.
So the last thing I want to show is a simulation of these of this mammatus cloud, which was carried out some years ago by Ravichandran. And that's my conclusions. Thank you all.
Any questions?
With context to one of your previous slides about GPGP, so I often see news headlines mentioning that they find bacteria or some other microorganism that can dissolve plastic, that can consume plastic. And I think a few years ago, the news made the headlines that an Indian found a way to use plastic to lay roads. And it also claimed that we will eventually run out of plastic if this method is adopted. So among all these headlines, why hasn't any of them come to fruition?
Come to flotation.
Come to fruition, like why hasn't this
fruition?
been? Yeah.
Okay. I don't know, like people should work more on it and make things happen, that's all. We have to get more organized about it. The point is that, suddenly, if you look at human evolution, okay, like things have been slow, and the last 20, 30 years, everything has been so fast. The world population has doubled in the last 20, 30 years. I think since you guys were born, it would have doubled. So like suddenly we're doing double of everything. We're putting double plumes and all. And then like the consumption has increased of plastic and things. So we've created so much plastic that we yet don't know what to do. So we're responding. So one positive way to think about it is that we're responding, but it's taking time. But we need to do it faster. Like if we want global warming to come down, we have to move a lot faster than we are moving. So yeah, we need more people in this game. And what I'm saying in the following is just a personal view. But I feel that if climate studies was very popular among young people, which it's not, if it was very popular among young people, we could do better science. I'm talking about India. Elsewhere, like many people go into it. But, here we'll choose like computer science or medicine or something and not study, let's say, geography or things which have to do with climate science, environmental science. Nobody, like, very often people don't choose those subjects. So I think that should increase, and we should actually get more awareness and move faster. This is just a personal view.
Thank you.
The last simulation that you showed, so there is something like a shadow region at the center in the trajectory of that non-spherical object that is falling through.
Where's the thing?
Yeah, this one. So
There's no shadow region.
So there's a central region where this trajectory is not covered. So what does that mean?
That's how this trajectory is. This is just a solution. There are other solutions where it may be going through that. We have other solutions where it will make a flower like this, so it will touch the center. It's just dependent on the initial condition.
Or if you run this for more iterations.
No, this you keep running forever, you'll get this much only. You'll get that nice hole in the middle. You can run it for hours and hours and hours.
Does it have a physical significance? What does that mean?
So basically, like, these are all, flows where there is a certain integral of motion, like certain constant of motion. It has to obey that. That plus the initial condition will just make a variety of trajectories happen. So each time you start with an initial condition, you're fixing that. So yeah, it's a technical reason, but that's what it is. More questions?
Ma'am, in the slide where you showed pipe flow and you showed the three dominant regions formed, contours of three dominant regions, the question is the physical domain is it's axisymmetric, right? So
Yes.
everything is very symmetrical there.
Yes.
Where does asymmetry come from?
Very good question. It comes from instability. So the point is the following. I mean, this is just a general point in fluid dynamics and everything. You'll see that certain patterns come up again and again and again, not only in fluid dynamics, but even in solid mechanics. Like if you see a tree, the tree trunk should be like flat, right? But you see patterns of a certain size. You always see length scales which are selected. And another very nice example is this thing called aeolian sand ripples. So like suppose I start out with sand which is just flat on the ground, like in a desert. Okay? Why do sand dunes form? It should be flat, right? Like that's the lowest potential energy. Whereas like you get ripples, certain patterns, and you get dunes. So you get patterns which seemingly come out of nowhere, but they're not coming out of nowhere. What is happening is that in all of these situations, the axisymmetric solution stops being stable. And other possible solutions which are not axisymmetric, which have certain wavelength, become dominant. So like when they become dominant, this one disappears and that one comes up. So like you need to do a bit of maths to get this, but it's a bifurcation. You can think of it that way. It goes through a new solution when the flat one or the easy or homogeneous one is not an answer anymore, or it's not the most stable answer. So think about it this way, like what do you think of when you think stability? You think, is it the bottom of a valley or top of a hill, right? So if I put a ball at the bottom of the valley, then it will, and I perturb it slightly, it will come back to the bottom. But if I put it on top of a hill, it will roll down. So now imagine that the homogeneous state used to be a bottom of a valley, but at some Reynolds number, it became a top of a hill. And then another one which had patterns in it used to be top of a hill. Now it's bottom of a valley. So the solution runs from here to there. Does that answer your question? Not an easy question, not an easy thing to answer, but yeah.
Just a curious question. What shapes clouds? Do we have any answer?
We have certain answers. So Rodam Narasimha, who used to have a cloud in the lab, he could actually like make clouds of different shapes. So basically it depends on how you model the speed at which things are coming, and how the phase change occurs, the concentration, and many such things. So he could make tall clouds, short clouds by manipulating these things, by manipulating the heating, which will determine the temperature change and things like that. So like it depends on all of these parameters, and it was more of an art than a science. Like he just had a sense for which knob to turn to get which cloud. So like there is things to be done in cloud shapes, and people do study them. And also clouds agglomerate and make big continental size clouds. So cloud shapes are a very good question.
How do the size of the hail, is it affected by the vertical height of the clouds?
The size of?
During a hailstorm?
Size of a rain.
Hail.
Hail. Yeah. It's affected by that. And it's affected by the turbulence.
But
and
does it depend on the cloud condensation nuclei or something?
Yeah, it depends on that as well. So for example, people have done these measurements. So in IITM Pune, Indian Institute of Tropical Meteorology, they have access to a little aircraft which flies through clouds and measures things. So there, they've measured things on polluted cities and on clean cities, clean places. So on a polluted city, because the aerosols are so many, lots and lots of droplets will form, and they won't rain because they'll never become big. Only when you're big enough, you'll fall, right? So you have to agglomerate, and if there's too many of you with too little size, you'll never touch each other and never grow. So you need that to happen to fall, and so the height matters, and hail especially, if it's very tall, then only you have very icy particles forming rather than water droplets. Shamriddhi is an expert on that, so ask him. But yeah, these hail things, they grow big, and then they can fall super fast. And if they're falling from a great height and they're still inside the cloud, they can collect other droplets and grow as they fall. So they grow a lot by gravity alone.
Another question, unrelated to this. So one of the AI scientists have been propagating the idea of stratospheric aerosol injection for climate change. So what are your opinions?
Personally, I'm terrified of geoengineering, but there's no point me sitting here being terrified in a corner. It is happening, and it's happening in big ways. This stratospheric cloud to cool the atmosphere is one thought. I think if people can do amazing computation, they know what they're doing, then it's worth trying, but there are dangers. And they're also trying this plankton I showed you, right, which drinks carbon dioxide. They're trying to make effectively farm plankton all over the ocean. So that will drink up all the carbon dioxide we put. So my personal view is, can we put less into the atmosphere? But geoengineering says, let's just do what we do, and then we'll get other fixes, which is winning. That's what is going to happen. There's even big things, big structures they build, which drinks the atmospheric air and eats up the carbon dioxide and throws cleaner air. So lots of such geoengineering things are already being thought about and worked on. So yeah, only time will tell whether it's a big disaster or not. I'm hoping that we do it smartly and it's not.
On a related note, Rama, Chandan Rocky from in the internet, he's asking, can clouds be artificially made, and what are your thoughts on cloud seeding?
Okay, so yes, clouds can be seeded artificially. Artificially made is a lot harder, but they can be seeded, and definitely that will create rain. What are my thoughts on it? Again, very similar to the previous question. So it's true that we can make rain somewhere, but it can become a big political issue also. Imagine there is rain clouds moving from country A to country B, and before it reaches country B, country A has rained it all out. So then that can be very sad for country B. And yeah, do you want to play with all of this so much? I don't know.
And probably related to what was already asked, what controls the extent of the clouds, not just the shapes?
Again, a hard question, but it basically depends on how much is evaporating from the ocean, how it's agglomerating, where it's moving, And is it moving towards other clouds or away? So it's a hard question, but it broadly is that. And we know that in monsoon time, like how it moves, we have some sense of how clouds move.
Yeah, this could be entirely unrelated or could be very much important. Before I frame my question, I want to understand one thing. While explaining that example of turbulence on a table or a flat surface, you mentioned that even a laminar flow is a solution of Stokes equation.
Of the Navier-Stokes equation.
Yeah, Navier-Stokes. I know little to less about that Stokes equation. But answer me this: whether a solution which is entirely counter, what we say, intuitive. For example, a particle coming out of, let's say, some source goes back entirely to the source is also a solution of what we say, Navier-Stokes equation.
Under certain cases, it can be.
Yeah. So since now that I have formed this basis that this equation is resulting solutions from like from one end to another end of the spectrum. Now, if that is possible, could it be true that because there are so many infinitely high number of solutions, it is only probability that is playing role? The extreme edge solutions are very less probable, and the ones in the center, which what we call turbulence, is highly probable, and only that is the reason why we see turbulence instead of being dependent on so many other things. Could that be?
Yeah, intuitively what you said is correct. So like, let's imagine that there's an infinite dimensional phase space. By phase space, I mean, let's take a pipe, and at every point in that pipe, I give a velocity. I give 3 components of velocity, and that is a function of time. So now I have an infinite dimensional phase space defined by the velocity at every point, right? There is so many possibilities, but turbulence is a small subset of that infinite dimensional phase space. It's also very, very, very big dimensional, but it's a subset of that. So that is called a strange attractor. In chaos language, it's called a strange attractor. So wherever initial condition I start from, it will collapse onto this thing, which itself has huge variety. Like it could have this 6 waves around the thing. It could have 4 around. It could have a variety of such solutions. So it has a range of things which it keep exploring inside that subset. So the Navier-Stokes attracts it to this attractor.
Any more questions? If there are no more questions, let's thank the speaker once again. And
Thank you
please
all.
join us over coffee.
Thank you.